All right, in this problem, we're doing a retrosynthesis. We know we started with a methyl cyclohexane. It has no functionality on it so far whatsoever, and we're going to end up with a ketone and an aldehyde. So the first thing to figure out kind of the last step that went on before we got to these products, I'm going to think ozonolysis. The reason is because we have this linear molecule that came from this ring. And the thing that we know so far that best breaks up a ring and forms these double bonded oxygens is ozonolysis. But we need to figure out the products that came before this. So let's count the number of carbons on this molecule, on this ketone. We have 1, 2, 3, 4, 5, 6. All right, so that's looking good so far. I have 6 carbons that can form a 6-membered ring. And the way I would do that is I would kind of try to stitch together this first carbon with this 6th carbon to form a hexane, right? So that would look something like this. All right, so the step before this, okay, would have been this 6-membered ring. All right, and then I'm going to label the carbons on here. We have 1, 2, 3, 4, 5, 6. Okay, and we know that ozonolysis breaks the ring where there was a double bond. Well, and it forms these double bonded oxygens in its place. So the double bonded must have existed between carbon 1 and carbon 6 because that's where it was broken and it formed each of those oxygen double bonds there. But we also have a doubly bonded oxygen at O. So that leads me to believe, not at O, excuse me, at carbon 5. So that leads me to believe that there must have been something on carbon 5. So if I draw a double bond off of carbon 5 right here, I can see that I would also, through ozonolysis, create this doubly bonded oxygen on the linear ketone over there, and also I would end up with an aldehyde. All right, so this is the molecule that led to this from ozonolysis. So let's go ahead and write in that step right here, ozone and CH3 2S at negative 78 degrees Celsius. Okay. So at least I have a molecule that looks like my starting molecule, but it has these, it's an alkene. It has these double bonds, and I need to figure out where those came from. Well, let's start with this one. I don't know if I should start with this one or this one, but I'm going to just choose this and see if it works later. And now I need to figure out how did I get to that step. How should I do this? Let's go like this. Okay. Well, in order to form a double bond, I can do an elimination. I could start with a halogen in that position and do an elimination and end up with a double bond. The question is, where do I want to put my halogen? Do I want to put it here? Or let's use a different color. Do I want to put it here, for example? Okay. Well, let's consider both possibilities. If I did an elimination on this halogen, it could form a double bond on this side and on this side. And both of those would be stable alkenes, and they're relatively the same in stability. So that wouldn't give me this product alone. However, if I use this halogen in this position, it can't form a double bond over here because that would make this carbon have 5 bonds. So it can only form a double bond over here. So I know that the halogen needs to be in that position. Okay. So how do I come from a halogen in this position and form this double bond? Well, I can do an elimination just to make sure that we can avoid carbocation rearrangements, even though we wouldn't really see any here. I'm going to do an E2 elimination. So I'm going to use a strong base in this case. I'm going to use sodium ethoxide, let's say, with ethanol. This is a strong base, but it's also a strong nucleophile. So just to make sure that I'm doing an elimination and not trying to do a substitution, which is possible here because I have a secondary halogen, I'm going to go ahead and add lots of heat, all right, to make entropy prefer elimination. All right, so now I know how to get to this molecule. I need to figure out how did I form this. So how did I get the halogen in there in the first place? We have several ways to add halogens. One way is the radical reaction adding Br2. We also can add NBS with light, or we can use HBr with light. All right, let's consider each of those possibilities. NBS would destroy this double bond, so we know that we don't want to use that. Now, Br2 we can put on something that doesn't have a double bond, but the problem with bromine is that it could add to any of these secondary carbons. All right, so we wouldn't get bromine in just this position. However, HBr with peroxides and light would only add bromine to either this position or this position because it adds bromine to the carbon adjacent to a double bond, to the vinylic carbon. All right, and whether we add bromine to this side or this side is the same because this is a symmetrical molecule. Also, this molecule, we could have formed this and thus our final product if bromine was either coming out or going in. So we can have a racemic mixture of this and we could still get the same product. All right, so I'll just go ahead and write plus enantiomer here, since this is in fact a chiral center. Okay, so we know that we can use HBr, peroxides, and light to make sure we get a bromine next to our carbon double bond there. All right, so the step before that would have just been this, before I put the bromine on there. Okay, so far we've taken care of getting this double bond. Now we need to figure out how to get this double bond. Because initially we just had a singly bonded carbon there. All right. Again, we know that we can form a double bond from a halogenated alkane by using elimination. So again, I'm going to use E2. But now I need to figure out where was the halogen in the first place? Was it right here? Let me do this in a different color. Off of the methyl group like that? Or was it off of the ring like that? Let's consider each possibility. If this were the case, if it were coming off of the methyl group, the problem with that is that it would be in a primary position. And primary is most liked or most preferred by SN2. And it would be really hard to get E2 on a primary halogen. This halogen, however, is on a tertiary position, and it's very easy to do E2. So let's go ahead and put the bromine here. But we would have one more problem. When we do elimination, we could form a double bond here, or we could form a double bond here. Actually, this is the more substituted double bond, and this would be more stable, and Zaitsev elimination would prefer to put the double bond here. So how can I force it to put the double bond here? I could do Hoffman elimination. So I want to do Hoffman. And we can do that by using a big, bulky base. And it has to be a strong base in order to do E2. So I'm going to use this tert butyl group. Oops, I need an oxygen. Oops. There we go. Can you see that? All right. So since this is a big, bulky base, there's too much sterics for it to go in and form this double bond, and it's going to, in fact, prefer to form this bond right here. All right. Now, again, we don't need to concern ourselves now with stereochemistry because this is not a chiral center. All right. So although we could have had enantiomers here, we could have produced those enantiomers through this process. from either this bromine coming out or going in, because this is a symmetrical molecule and this is not a chiral center. All right, so the last step is we need to figure out how we got the bromine in that position. Again, we can use radical reactions, and we need to figure out which one we want. We know that we can't use NBS in light because we need a double bond to do that. Same thing with this reaction with HBr, we need a double bond somewhere in the molecule. The only thing that can add functionality to a molecule that has nothing but single bonds is to add bromine and light. And that works because we know that bromine is going to add, when it forms a radical, it's going to form a radical to the most substituted carbon and then add the bromine in that position, which would give me bromine in this position. All right. And that is how we come from the methyl cyclohexane to our ketone and an aldehyde.